Uh, Hello everyone. Let's wait 2 to 3 minutes for others to join. All right, we'll start. I'll just share my screen. Okay, so I hope I'll be audible. Welcome to this uh, brief extra session on NPTEL NOC24 EE-28 Signals and Systems. This will be the last live interactive session um, from my side for this course. Uh, Professor Hitesh Shrimali and Professor Kushal Keshav were the course instructors of this course, and The schedule for the sessions was Sunday, every Sunday, 3 p.m. to 5 p.m., right? And these lectures were also recorded, and you would be having access to all the recordings, probably including this uh, recording for this extra session as well. Okay, so yeah, this is me. Again, the guidelines, the guidelines were made keeping in mind that uh, many students would join this meeting live and readily interact and ask questions. But yeah, I mean, uh, it wasn't that interactive as I intended. So, anyways, uh, do let me know if you have any queries uh, from any of the sessions. Okay, you can either mail me directly or you can just, I mean, drop a comment below the video. Okay, below the respective video, and then I'll try to respond as soon as possible. So the prerequisites of this extra session will include all the lectures of the course. Okay, so mm, I'd planned to conduct this extra session for clearing all of your doubts, if any, in this session itself live. But since there is hardly anyone in the meeting live, so let's do one thing. I'll uh, cover or take the sample problems randomly from any of the topics, and uh, then if you have any doubt we can discuss that separately. Okay, so let's do one thing. um, in the week 6 I'd given you an example as an assignment, right? And although I wanted you all to attempt that yourselves, but I'll utilize this time in extra session to cover that. Okay, so this would be our sample problem 1, right? So I'm taking this problem from the last week's content. Okay, so in fact, yesterday we had a live session, right, in which we solved problems from the Z transform, right? We solved quite a many, I guess 8 to 9 problems from Z transform and the region of convergence. So this is one more such problem. So consider that you are given a signal x of n and it's equal to a raised to the power n uh, in this range, right? When n lies in this range, and yeah, a is greater than 0, right? And it's equal to 0 otherwise. You are supposed to find x of z. Okay, so let me attempt it and you can attempt it as well simultaneously. So yeah, we know that your x of z is given by summation n varies from minus infinity to plus infinity, right? I'm using the definition of Z transform, right? since we were supposed to find this x of z. X of n, z power minus n, right? This is how we define this x of z. So now what? Our limits will change since the given discrete signal x of n is equal to 0 for some values of n, right? Let's incorporate that. So your x of z would be equal to, see, it is equal to 0 for values of n that don't lie in this range, right? So from minus infinity to minus 1, this would be 0, right? When n is minus infinity to n equal to minus 1. In this range, your x of n is 0. So I'll use that. So my lower limit will be from n equals to 0. And similarly, beyond this n minus 1, for example, n plus 1, all such values, the signal is again 0, right? So this is n minus 1. Only in this range, the signal is non-zero. So, and what is the signal in this range? In this range, our x of n is a power n, right? So I'll substitute that. And then our this z power minus n, right? Now, this is a sum of finite terms, right? So let me first rearrange this sum. N equals to 0 to n minus 1 a z power minus 1 whole raised power n, right? I can rearrange it in this way. Now, what are the terms? The terms that I have are, first term would be a z minus 1 raised to the power 0. Now, since this a is not equal to 0, right? It's given that a is greater than 0. So this one is 1, right? Similarly, the second term would be a z power minus 1 1 plus a z power minus, sorry, 2, and then so on. Right. Now, what is the result of this finite sum of a GP? Right. This is a geometric progression, right? And it's actually a finite geometric progression. So the result that you will use will be based upon this uh, R, right? Is your R, I mean to say this, is it less than 1 or is it greater than 1, right? In this case, uh, our a is greater than 0. We'll assume that this a by z is less than 1. Okay. If you assume this a by z is less than 1, right, your a is a power minus 1 is a power z is equals to r. We'll assume that this is less than 1. So if that is the case, then what is the formula? Let me write the formula. Okay. This is the formula. Sum of n terms of a GP is a, the first term, multiplied by 1 minus r raised to the power n all divided by 1 minus r. Right? Your r is less than 1. So your x of z is equals to, now this is 1, right? So 1 minus r is to the power n. R is a z power minus 1, right? And fine. In fact, how many terms are these? Wait, see, I need to raise to power this by number of terms, right? If the number of terms were n, the exponent of r was n, right? Now, how many terms are these? How many terms are these? This exponent would go all the way till capital N minus 1, right? Starts from 0 and goes all the way to n minus 1. So these are n terms, right? So exponent would be capital N, whole divided by 1 minus r, right? 1 minus a z raised to the power minus 1. Now we'll simplify it further. Our x of z would be 1 by z to the power capital N minus 1. Z power capital N minus a power capital N z minus capital A, right? Yeah, I have, this is a by z, right? After rearranging this, you will get this, okay? Okay, let me draw a different page. Now, your x of n was a finite length, right? Let me write it as well. Your x of n is of finite length, right? So what can you comment on the ROC? In fact, the reason I took up this example was I wanted to discuss one property using a detailed example. Okay. And this example falls in that category. When x of n was of finite length, what did we, I mean to say, uh, concluded on its ROC? Let me show you that. This was your week 12, right? And in week 12, we saw this property, right? If x of n is of finite duration, then the ROC is the entire z plane, except possibly z equals to 0 and or z equals to infinity. Now, x of n is indeed of finite length. in this case, right? It is a finite duration. But in fact, since x of n is 0 for n less than 0, ROC will extend to infinity, right? Our ROC will extend to infinity. It will extend to infinity since x of n is equals to 0 for n less than 0, right? Now, what about the other end? Will it extend all the way to 0? Since x of n is non-zero for some positive values of n, the ROC will not include the origin, right? So let me write that. So your ROC will not include it will not include origin, right? It will not include origin. And the reason you will cite is because since your x of n, it's non-zero, right? It's not equal to 0 for some positive values of your this n, right? So it is then evident from this expression that we see that there is a pole of order n minus 1, right? A pole of order n minus 1 at z equals to 0, right? And ROC does not include pole, right? So you can use either of the two uh, reasonings to conclude that the ROC will not include origin. Now the n roots of the numerator polynomial, here the numerator is of order n, so it will have n roots and correspondingly will have n zeros, right? So uh, let me write them as well. Your zeros of x of z, right? Uh, uh, you have n such zeros, n zeros, right? The reason is because your numerator polynomial has n roots, right? Your numerator polynomial has capital N roots, right? From this one. So what should be, suppose in general, if we have zk as the kth zero of this x of z, that in general would be equal to a times exponential of j 2 pi k by n, right? Where your k takes value 0, 1, all the way till n minus 1. Note, these are n such values of k corresponding to your n zeros of x of z. I mean, I wrote this because we know, right? Z power n minus a power n. The roots of this equation are given by this. That's why I wrote it directly. Fine. Now, what about see, there will be poles as well, right? So what would be the poles? There will be poles. Where will the poles be? That is actually an interesting one. Poles of x of c. First, the question is how many poles will this x of z have? The second one is where are the poles located? Okay, so uh, attempt this for 2 minutes, then I'll proceed. Okay, so it turns out that the root for k is equals to 0, right? It cancels the pole at z equals to a. Okay, so there are no poles other than at the origin. Okay, so uh, the remaining, I guess I should write that as well. The root for k is equals to 0 cancels the pole at z equals to a, right? Consequently, there are no poles uh, other than at the origin. Okay, so your remaining zeros are z power k, and z power k is equals to a exponential j 2 pi k over n, right? Note that k will now run, I mean, will not include k equal to 0. So it would take value from 1, 2, all the way till n minus 1. So now we have n minus 1 zeros. Okay. And for k equal to 0, when k was equal to 0, this zk was a, right? That cancelled with this. Okay. So we don't have a pole uh, at z equals to a, and we only have poles at origin, but as a consequence of that, we have only n minus 1 zeros, right? One of them cancelled with this pole. So, and those n minus 1 zeros are located at z power zk given by this, where k runs from 1, 2, so on all the way till capital N minus 1, right? In fact, if I were to draw the pole zero pattern, it would be somewhat like this. Let me draw that. Let's draw pole zero pattern for this problem. Let me draw that unit circle. It's not that good. Yes. Fine. This is your unit circle. And these are your n minus 1 poles. Okay. There are n minus 1 poles located at this, right? Corresponding to this term. And where are your zeros located? You have your, uh, I mean, this pole, the pole at z equal to 0 is of order capital N minus 1. Sorry, I mean, there is one pole, but that pole is of order capital N minus. What about zeros? We have uh, n minus 1 zeros, right? Right, I mean, this is your z equals to a, but there won't be a pole at that location, right? We already discussed that. The root for k equal to 0 cancels the pole at z equals to a. right? This is uh, n minus one order whole, and the rest are your n minus one zeros, right? These are your n minus one zeros. We are done with this. So where is so now what about ROCs, right? The whole point was about ROCs. So ROC would be all the values of Z, right? All the values of Z except where this pole is lying. Okay. ROC won't lie at origin in this case. ROC will include infinity in this case. Okay, so this was one such example. Now, uh, a small assignment for you all. I wish you were present in the meeting so that we could discuss that as well. But since you're not, I have a small assignment for you. Think of a problem in which ROC does not include infinity but includes origin. There are two questions actually. Is this scenario even possible? ROC including entire Z plane, N- but origin, I mean, including origin. Okay, entire Z plane, including origin, but except infinity. Let me know if this is possible. If it is, why? If not, why not? Okay, so this is an assignment for you. What else did I have planned? Yeah, I mean, these were your real and imaginary axes, right? And this was your unit circle. ROC, ROC, uh, for this, um, I mean, ROC consists of all values of Z except Z equals to 0. Okay. Okay. So now the second question. This is in fact something that we had left as an assignment at the end of week 6 live interactive session. Uh, I mean, I was uh, short of time at that point of time. So I left this as an exercise for you all. But now, since I'm not getting any questions or doubts in this extra session, what I'll do is I'll discuss this question as well, since I had not discussed this in the week 6. I mean, I had planned to discuss this at the start of week 7, but since nobody asked about it, so I skipped it. So let me first write. This would be the sample problem 2. Okay, and refer to week 6 uh, live interactive session slides. Okay, yeah, I mean you'll get to know. Uh, Navigate to the end of the slides, and there you'll discuss. I had given you the slides, but I had not discussed that. So now I plan to discuss this right now. So first, I'll again, in case you have not already attempted this problem, attempt this and then I'll start doing it. Okay, I'll wait for 5 minutes. Try to find x of t convolution v of t. All right, I guess I gave sufficient time. Uh, let's see how we proceed on this one. So we are given two signals, right? Here x of t and v of t. Now this x of t is actually a piecewise defined signal, right? Piecewise defined function. So this is the piecewise defined representation of x of t, right? It is 0 when t is less than 0, and it's again 0 when t is greater than 3. But between 0 to 3 in this region, see, x of t is equal to, uh, it's a linear function. Moreover, it's equal to 1 at t equals to 3, right? And it's equal to 0 when t is equals to 0. So It's simple. This t by 3 satisfies that, right? And t by 3 is linear. So that's why it's t by 3. So we are done with this. What about this v of t? It's 0 when t is less than minus 1. It's 0 when t is greater than 1. But when t is between minus 1 and 1, the value is 1, right? So that is what I wrote. So now we have, now we'll split this into 5 cases. Okay. How will split up? Case 1 would be when this t is less than minus 1, right? I mean, the point is, while computing this x of, I mean, uh, you'll understand the motivation later, why we split the intervals into 5 parts. Okay. First, let me tell you what those intervals are. First one is when this t is less than minus 1. The second one is when this t is from minus 1 to 1. And the third interval is when this t is from 1 to 2. Okay, till here, right? This part might not seem that intuitive, but when you'll utilize the definition of convolution, you'll understand it why we split uh, the interval into 2 parts, right? Into these parts. So, so this part is from 1 to 2. Okay. So this part, and the other one is from 2 to 4. This part, and then it's beyond 4, right? So all these cases. So it'll take up case 1 first. What happens in case 1? Our t is less than minus 1, right? So see, this is how we write convolution, right? X of lambda v of t minus lambda. Now, since this t is less than minus 1, since this t is less than minus 1, uh, t would be somewhere around here, right? So what about this? Uh, should I say? Just a second, okay? Yeah, we have this x of lambda, right? This x of lambda would simply be substituting t by this lambda. Okay, but what about this? We need to shift this by lambda in this direction, isn't it? And when we shift that, uh, this would be, I mean, in fact, that's the other way around. See what you will do in this case. V of t is this, right? I mean, I'll do everything in lambda domain, okay? Since I have drawn this scale in lambda. So what would be V of lambda? Simply changing this. What would be V of, I have to reach here, V of t minus lambda. What would be V of minus lambda? V of minus lambda would again be same. Why? Because this is an even function, right? And if V of t is equal to V of minus t, similarly V of lambda is V of minus lambda. So it's same. But when I use V of t minus lambda, and t is less than minus 1. So at least it would shift it by a magnitude greater than minus 1, right? So, so yeah, it would reach to a point here, right? This t, right? This, I mean, the center point was originally at origin, right? Now it's at t, isn't it? And this t is less than minus 1. So Let's take the worst case scenario when this is -1, even though it won't take the value -1. When this is -1, here it was 0 plus 1, 0 -1. I'll do uh, t plus 1, t -1. When t is -1, this would be -1 plus 1, 0. When t would be equal to -1, this would have coincided with this point. So t less than -1 would mean that it would be this point would always be mapped to a point less than this, right? It would be to the left of this origin. So the point that I'm trying to emphasize is that the product of this x of lambda with this would always be 0, right? Because only when they both would have been non-zero for some values of lambda, this product would have been non-zero, right? But x of lambda is 0, right? And v of t minus lambda is 0. So either this is 0 in some domain or this is 0 in some domain. There is no lambda for which they both are non-zero, right? So we conclude that x of t convolution v of t is equals to 0 for t minus 1. I mean t less than -1. Now the case when t is uh, from -1 to 1. We already said that when this t is -1, this point would correspond to this exact origin, right? This would correspond to this exact origin. And I mean this t plus 1 point, isn't it? Wait. When this in this interval, what about this x of t? When t lies between -1 and 1, your x of t is okay. So x of lambda is simple, right? X of lambda will remain same. But what about this v of t minus lambda? Again, v of minus lambda would be v of lambda. And then we need to uh, delay shift the signal by t units, right? Where t is from -1 to 1. So convince yourself that uh, this t, right? V of t minus lambda would in general take this form relative to this x of lambda, right? And so this, uh, if this is v of t minus lambda, this portion won't contribute. Why? This won't contribute because x of lambda is 0 in this region. Only this portion will contribute, right? So I need to integrate it from this is t equal to 0 point, right? I need to integrate till this point, and this corresponds to t plus 1. So t equal to 0 to t plus 1. That is what I did, right? I integrated it from t to t plus 1. And in that region, what was your v of t minus lambda? It was 1, right? So instead of v of t minus lambda, I used 1. And your x of lambda was lambda by 3, right? I'm following this definition. And I need to integrate that, right? So by taking product at each point. So x of lambda is lambda by 3 and then d lambda. So your lambda by 3 when integrated would be lambda squared by 6, right? And limits of the integration would be from 0 to t plus 1. So this would be t plus 1 square all divided by 6, where t lies in this range, -1 to 1. Okay, I hope this is clear. Now we'll take the other scenario, right? When this, yeah, this is in general, right? Now I'll show you two extreme cases so that it might, I mean, you could intuitively find it simple. When T, and in fact, in general, whenever you are given such problems, try to see what happens in extreme cases and then try to visualize or uh, apply your intuition, what happens in between. Okay, this one I already gave you intuition, right? When this T is -1, this would be somewhere around here, right? This center point, and this, right, this situation corresponds to when T is -1. This would be exactly mapped to this. What about when this is T is 1? When T is 1, when T is 1, T is the center point of this. So when this T is 1, it would be somewhere around here, right? This would be V of T minus lambda when T is equal to 1, this extreme point. Okay, so it was till 2, right? When T was 1, because we need to take that T plus 1 point. So this is done. The other way would be now, we saw a case when this tip, right? When this tip reached 2. The other case would be when this tip reaches exactly at 3, right? That would be when this product in fact is maximum V of T minus lambda x of lambda, right? Because uh, it would be multiplied. I mean, this would be x of lambda, and this would be V of T minus lambda, this being 1, corresponding to what? This would be corresponding to T equal to 2, right? Because at T equal to 2, this would be T plus 1, and this would be T minus 1, right? So that is why the next interval is till that point, right? From this 1 to 2. So it would I mean, it would start from here till 2 and go all the way till here. And this is 1. Okay. So this is something that you need to visualize. Okay. If you have any doubts, you can let me know. We can discuss the individual cases as well. So now what happens in this range? We need to integrate this whole, right, from T minus 1 to T plus 1, right? It's a range bounded always in between. In the leftmost limit, this would take this value, right? And in the rightmost case, this point would correspond to this point. So in any of the cases in this interval, in this interval, sorry, in this interval, 1 to 2, this would see when T is equals to 1, when T is equals to 1, I guess I should draw V of T minus 1, right? V of T minus lambda, I'll draw V of, since this would be same, right? This is same. The only relative position of V of T minus lambda would determine what this product would be. When this T would be 1, this would be V of T minus lambda, right? Because this center point would be corresponding to T equal to 1, and this would be T equal to 0, T minus 1, and this would be T equal to 2, T plus 1, right? And the other extreme is when this T is equals to 2. In that case, We'll have this form, right? This center point would correspond to t equals to 2, right? This one, and this is your t plus 1, and this is your t equal to 1, right? Here t plus 1 was 3, the right extreme, and this is t equal to 1, your t minus 1. I hope this was clear. And in this range, again, v of t minus lambda is 1, right? And your x of lambda is lambda by 3. So limits are now t minus 1 to t plus 1 based on the value of t. Again, lambda square by 6, but the limits are, instead of having it from 0 to t plus 1, because there was some portion cancelled in this interval, here the entire portion remains. So from t minus to t plus 1, you get this 2t by 3, right, in this interval. Now what about the other case? In the other case, uh, what happens in the other case? When this t is 2, right? When this t is 2, when this t is 2, when this t is 2, this would correspond to this, right? This v of t minus lambda instead of this becomes this when this t is 2. Okay, so integral of t minus 1 to 3, because as your t increases, there would be some portion getting outside this range, and this won't contribute to the product, right? So we are not interested in that. We are, see, for example, when t is 3, when t is 3, it would start from this t equal to 2. So we need to consider only this part, right? Because only this would contribute. This part, in this part, the x of lambda is 0. So this is a no. Okay, here the product is 0. So that's why we chose the limit from 2 to 4. Okay, in this, our t takes, I mean, the non-zero, the integral is non-zero from t minus 1 to 3, right? Please make sure you understand why you chose this upper limit as 3 and upper limit as t plus 1 in this case. If you have any doubt, you can let me know. We can have one-to-one interaction. So lambda square by 6, because yeah, again, see, the integral is same. The only thing that changes is the limits, right? Now we need to consider only till 3 upper limit. Beyond that, it's of no use. Even if you take it after that, x of lambda is 0 beyond 3. So you split this up to 3 to t plus 1. It was 0 here. So anyways, this was not contributing. So instead what we did was we changed the limit to 3. So here now, this is what we get. Minus times t square minus 2t minus 8 divided by 6. And in this interval, okay? Now the last interval, when this t is greater or equal to 4. When t is greater or equal to 4, uh, I'll use first the lower limit of t in this case, which is 4. When t is 4, this corresponds to a case when a tip, this tip matches with this, right? And your t is 4, right? This case. Even in that case, this product is 0, right? Why? Because, I mean, there is no common lambda in which both are non-zero. Either this is non-zero or this is non-zero. When this is non-zero, v of t minus lambda is 0. When this is non-zero, Rx of lambda is 0. Okay, that's why the product would be 0 beyond this. And there is no interest in taking higher intervals, right? Because once this dash, see, this v of t minus lambda was slowly navigating, right, as we increase t. But beyond this point, however high we increase t, our x of lambda is 0 throughout, right? So what we did was we considered in general an interval t greater or equal to 4, and all those uh, these products would be mapped to 0 when t takes a value greater or equal to 4. Okay, so in nutshell, this is how our convolution looks like, x of t convolution v of t for the 5 cases, right? Case 1, case 2, case 3, case 4, case 5. In when t is less than -1, it was 0. When in -1 to 1 interval, it was t plus 1 square by 6. In 1 to 2, it was 2t by 3. From 2 to 4, it was minus t square minus 2t minus 8 whole divided by 6. And when t was greater than 4, and in fact, I am very sorry for this. I should not use this equal to sign. Okay, it's only greater than sign here. Please mind, this is not greater or equal to. This is greater than. Okay, please correct this. That's why I have not used greater or equal to, because had I used equal to sign, these tip would match, right? There would be one point where I get this value 1. At least the product would take value 1, but that is not the case, right? For t greater than a, this will be very close to this, but not mapped to this, right? This tip. It would be very close to this, but not exactly this, somewhere here. So we are done with this. Now, what about this? The next question is your sample problem 3. This is your sample problem 3, and you need to find x of n convolution v of n. Okay, your x of n is this, your v of n is this. You need to find x of n convolution v of n. The previous example that I took was from continuous time case, right? This one is from discrete time case. Okay, please try solve this one. This means that your x of n is 0.5 minus 0.5, and then it's 0 throughout, right? So I'm not interested in that. This is corresponding to n equals to 0. V of n is equals to 0, and then it's 1, 1, and 1, right? What is the convolution x of n v of n? Please try to attempt this. Okay, I guess I gave sufficient time. So this is how we solve it. Let me first use color coding. This is your this color, okay? And this is your this color. Okay, this is your V of n. This is your x of n. I mean, one approach is to do this from definition. I'll leave that as an exercise for you. I'll instead use a shortcut here. Okay. And then what is your V of n? Your V of n is 0, 1, 1, and 1. What is your this x of n? Your x of n is x of n is zero point 0.5 and minus zero point 0.5, right? So first is 0, then it's zero point 0.5. Then so first term is 0 0.5, right? Your x of n convolution v of n. First term is 0 0.5. What is second term? Minus zero point 0.5, right? Why? Because sum of 0 and minus zero point 0.5. Sorry, I guess it took a row that I shouldn't have taken. See, now it's fine. First term is 0, second term is zero point 0.5, third term is 0, and then 0, and then this one, right? So let's write that x of n convolution v of n is equals to 0 corresponding to n is equals to 0, and then it's zero point 0.5, and then what is the sum of zero point 0.5 and minus zero point 0.5? That is 0, right? What is right? Guess I have made a mistake here. What if we do this by definition? Let's try that out as well. So you had this x of n, here's this color, x of n, convolution y of n, right? This was equal to summation, your k varies from minus infinity to infinity. Your x of k, I guess I would write it as v of k, okay? V of k, x of n minus k. Fine. And let this be, this is your y of n. So what is y of n? I mean, k can have values 0. So what happens corresponding to n equals to 0? What would be y of 0? Y of 0 would be summation over k, v of k, x of 0 minus k, right? This would be v of 0, x of 0 plus v of 0, x of minus 1, so on. In fact, I would take this right. For k equal to minus 1, this would be v of 1, I mean x of 1, right? And then we have here v of 0, x of 2. This is how our y of 0 is, right? Now, what terms are 0 in this? This term is 0. Why? Because x of 2 is 0. So only x of 1 and so see, since v of 0 is 0 throughout, all these would be 0, right? So you get this y of 0 is equals to 0. What about now y of 1? For your y of 1, you'll again compute summation over k v of k, x of 1 minus k, right? And in terms of this, y of 1 would be, okay, so this would be, okay, I'm sorry. See, we missed out one thing. Y of 0, although would be 0, but the reason would be different. See, when k is equals to 0, this would be v of 0, x of 0, right? When k is equals to minus 1, this would be v of minus 1, x of 1, right? Then it would be v of 1, x of minus 1, so on. Now, this is 0 y because v of 0 is 0. This is 0 y because uh, v of minus 1 is 0, right? I mean, yeah. And this is 0 y because x of minus 1 is 0. So that's why we are, I mean, our y of 0 is 0. But now when for y of 1, we have something slightly different. It would be, I'll start from v equal to 0 onwards because before that it's 0. So v equal to 0, I mean k equal to 0 would mean I have x1, right? And then v of 1 plus these terms are 0. Convince yourself. Plus x of 2, v of 2 minus k. Wait, v of 0, x of 1, v of 1, x of 0, right? Similarly, v of 2, x of minus 1. And then we have so on terms. See, this one is 0. These terms are 0. What about this and this? V of 0. Okay, v of 0 was 0. So this term is again 0. We are left with only this term. V of 1, x of 0. V of 1 and x of 0. So it's 0.5, right? So y of 1 is indeed 0.5. Let's do one thing, we'll evaluate till this. Okay, so we are done with this. We are left with these two. Y of 1, y of 2. Your y of 2 would be summation k vk x of 2 minus k, right? Then we'll write that y of 2 is equals to v of, I mean, v of 0 is also 0, right? So let me start writing terms from v of 1 instead. V of 1, when k is equals to 1, x would be 1, x of 1, right? 2 of 2 minus 1 when k equal to 1, plus v of 2 your x of 0, and then plus so on. These and these are 0. What about this and this? V of 1, x of 1. Your V of 1 and x of 1 is minus 0.5, isn't it? This is minus 0.5. What about the other V of 2 and x of 0? This and x of 0, zero point 0.5, right? So I'll write 0.5. This is 0, right? Minus 0.5 plus 0.5. So y of 2 is equals to 0. Now what about y of 3? See, we verified till here, right? First one was 0, and then it was 0.5, 0. Now we'll uh, determine what is the value of this for n equals to 1 to 3, right? Y of 3 would be summation over k vk x of 3 minus k. Right, this would be equal to we'll start from again v of 1, right? V of 1 when k is equals to 1, this is x of 3 minus 1. What is 3 minus 1? 3 minus 1 is 2. Similarly, and in fact this is 0, but anyway, then we have v of 2, right? V of 2 would correspond to x of 1, right? And then we have v of 3 x of 0 plus so on. Your y of 3 would be this term is 0. Why? Because this is n equals to 1. So at n equals to 2, x of n is equals to 0. So I mean your x of 2 is 0 from here. Okay, so this term is 0. What about this? V of 2 x of 1. V of 2 is 1. X of 1 is minus 0.5. So it's minus 0.5, right? What about this V of 3 x of 0? V of 3, 1, 2, 3, this one, and x of 0, this one. So this is 0, 0.5, right? So y of 3 is equals to 0, right? Yeah. So yeah, I guess then this is wrong, right? The correct sequence is this one. So I guess I'll delete this one. So now we use both the methods, right? It was anyway a good exercise. We use shortcut as well as we use this definition of discrete time convolution. Similarly, you will verify for this one, right? Verify yourself how y of 4 is minus 0.5. Verify this yourself, okay? So that's it, what I had planned for today. I'll end the session here, okay? Thanks for tuning in. And yeah, Any questions, you can just mail me. And if you have any feedback or any query, again, you can mail me on this same mail. Okay. Thanks. Bye. This would be the last interactive session. Yeah. All the best for the exams.